So to start out the afternoon, I'm going to present to you two papers, one that is published and one that is not. You have a copy of the published one, but not the one that's not. The one that got both of these studies were funded prior to the case series that Roger told you about this morning, where we basically debunked our entire hypothesis that there would be a common rheumatological disease that we could identify for Libby with a common autoantibody profile that would help us do exactly the kinds of things Ted was talking about, where we can come up with a diagnosis or a syndrome to begin to come up with markers and diagnostic processes as well as treatments. So that's why I'm going to go very, very quickly through this one, because I'm not sure that it teaches us anything new that we haven't already realized from the clinical data. But what it did was kind of scratch at the big data idea, the idea of looking deeper into our data and trying to come up with some commonality among these folks. So the paper had myself and Dr. Survey, Dr. Black, and Marv Fritzler, who was my rheumatology consultant from Calgary, University of Calgary. He's done a huge amount of work looking for autoantibodies as screening tools, the ability to identify patient groups that will respond to a certain treatment, or at least if we can identify the disease and we know who to treat. So he was very excited about this project when we proposed it, and it was funded by the Mountain West Clinical Translational Research Award process that came through a variety of Mountain States universities in this consortium. So our hypothesis was that there would be a unique panel of autoantibodies that would pop up in Libby amphibola exposed individuals that would help us identify this rheumatological syndrome. So what this was based on was our first study way back in 2005, where we had our Libby group and our Missoula normals. If you've ever been to Missoula, you know that's not possible. But we did have our Missoula normals, and we just looked at percent ANA positive at a 1 to 40 screening dilution, and we found that there was a much higher frequency of positive ANA tests at 1 to 40 in Libby compared to Missoula. What I don't show here is that the titers were also quite a bit higher. So we had a predominance of titers that were above 320, which is getting up into the area where it wouldn't occur in a normal population. So this was what was driving all of the work that we've done since then, really was seeing this screening information. The question was, when we published this paper, we said asbestos. And I have since then, from reviewers to all these other people, been trounced on for having done that, because Libby amphibola is not asbestos, according to the regulators. So the question was, does all asbestos, do all mineral fibers do this? So we did a lot of work in mice in order to test that question. So we used the C57 black 6 mice. We exposed them intratracheally. So we exposed them right down their trachea into the lung to saline, Libby amphibola, and National Toxicology Program intermediate chrysotile. And they went for 7 months, and that's something that's important with laboratory mice, is that it takes a long time for disease to develop, but it's not as long as people. So our latency in mice is about 7 months. Then we tested them for the anti-nuclear autoantibodies, the ANA test, which is our typical test looking for these autoantibodies. So anyway, we took these mice, we did this studies, and with comparing just Libby amphibola with chrysotile, we saw that the Libby amphibola drove the production of these autoantibodies, but chrysotile did not. The levels of ANA positive ANA tests in the chrysotile exposed animals was right where the unexposed animals were. Whereas 70 to 80 to sometimes 90% of the mice exposed to Libby amphibola had ANA antibodies. That really got me to thinking, because a lot of the papers that you'll read, it just says asbestos. And so we don't, most of the time, commercial asbestos is chrysotile. So we just didn't know, why hasn't this been reported before, that asbestos drives this autoimmune function? And so my hypothesis began to be, it's because not all asbestos does this. Chrysotile does not appear to drive an autoimmune response. Therefore, we had to start looking at other fibers and trying to tease this apart. And so where the slide would have been, is looking at tremolite, yes. Crucidolite, yes. Erionite, a non-asbestos elongated mineral fiber, yes. Chrysotile, no. So it began to look like it was amphibole, the elongated needle-like forms of asbestos or mineral amphiboles that do this. So that really was the baseline question we were trying to ask. How can we show this in people? How can we demonstrate that there's a very big difference between the autoimmune responses between two exposure cohorts? So this paper that we did get published looks at the Libby amphibole cohort from Libby and then the Mount Sinai steam fitter cohort that Jaime helped us put together. And one of the big challenges of this paper was to demonstrate to the reviewers that indeed the steam fitter cohort was entirely chrysotile or mostly chrysotile. We ended up having to say predominantly chrysotile. They would not let us say it was chrysotile, which I get that. Although we did provide some papers and literature to show that by and large it was chrysotile that they were exposed to. What we did then was, so we got the serum samples from the steam fitter cohort and the serum samples from the Libby cohort, and we sent them all to Canada to Marv's lab, where he analyzes a whole panel of these autoantibodies on a bead-based array. And he sent all that data back to us for analysis in order to tease apart and see if there were differences between these two cohorts. All right, so just to show you one of the studies that we attempted to do in humans to back up the mouse data was a work that I did with Peter Franklin and Allison Reed at Perth University. And what we did there was we didn't want to compare their crucidolite exposed group with American populations because they're different. And so we used the Busselton study. So the Busselton study was kind of like NHANES here in the United States in that it is a group of healthy people, a screening of healthy people in Australia. And so does this graph look reminiscent to what we did with Libby and Missoula? Very much so. So this is just the frequency of positive ANA tests. Again, this was, I think, at a 1:80 serum dilution, showing that this high frequency in the Whitnam cohort and Busselton. They did a lot, I'm not going to go through all the statistics that they did, but they did a lot of correcting for age, smoking status, sex, etc., in order to come up with an almost 5-fold risk of having ANAs if you were in the Whitnam cohort. So these were folks that were exposed both environmentally and occupationally to crucidolite asbestos due to crucidolite mining. So we do have that. But as of right now, I don't have any other human populations of known exposure to other amphiboles that we can work with in order to say, like we did in the mice, that all these other amphiboles drive autoantibody production in humans. I just wanted to mention cytokines mostly because I'm going to talk about it on the other paper, but we did the cytokines as well in mice. And what you see is that both, and Kinta can talk more about this tomorrow, but we see a very inflammatory process with both probably any kind of asbestos, where you get these inflammatory cytokines like IL-6. But IL-17, which suggests a more chronic immune response, immune activation, immune dysfunction that might be associated with autoimmunity, we only saw with the Libby amphibole at that point called 6-mix. So it starts to tease this apart, and we thought, oh, we're going to start to see this in people. We're going to be able to tease them apart based on their autoantibody profiles and their cytokine profiles. This is going to be great. This is just showing, again, this was an early study of amphibole lit from Libby, chrysotile from Mount Sinai, showing the difference in the ANAs, and then again, our studies with the mice. So different asbestos, different response in the mice, and we thought in humans. So these are the two cohorts that we're going to compare with these antibody panels. This was funded in 2014, I think. So it was a while ago, and this was one of my very first, this is gene's ability to see things, which is not numerically. I see things in a picture. So I had to have a picture. So I presented these data at the annual meeting of the funding agency, and showed that if we just compared the positive tests using a positive-negative cutoff for clinical diagnosis of all these different autoantibodies that are seen in different systemic autoimmune diseases, we saw two things. One, we see a lot more people having positive tests with libby-amphibold than we do with chrysotile. And we see some antibodies popping up with the amphibold that we did not see with the chrysotile. So this was my early visualization of what I was looking for. I was looking for a distinct pattern between those two populations. It looked good at this point. All right, so this is a paper then that was published, Analysis of Autoantibody Profiles in 2 asbestiform fibro cohorts. I couldn't say asbestos because the reviewer, who's beloved to me, said you can't do that. So here's some of the data. This is the exposure data, and what it does is it illustrates the difficulties of a cohort study where the exposure matrix was completely different. So for the Libby group, it was based on the Curtis-Noonan exposure matrix. And then for the steam fitters, it was based on the occupational exposure matrix for Mount Sinai. So very different. They're really not comparable in many ways. We could give the range of reported jobs in the cohort in fibers per cc. So we have that. But that's really all we have that's kind of comparable between these two groups. And then we had smoking data on the libby-amphibold group, but we didn't have smoking data on that. So it really illustrates how difficult this was to make this comparison. We were thrilled that we got it published because we think it illustrates some interesting points. So there's the box and whisker plots you guys can all get excited about looking at. And so what I want to point out is just a couple of visualizations here. If you look at a lot of these, the averages are about the same. Here's one that's different, histone and Smith. These are different lupus autoantibodies that are different. These are all myositis antibodies, and they're pretty much the same between the two and all quite low in the two groups. So then what the statistician did, who was Chris Barber, went through and analyzed all this in detail. He came up with these plots where the red dots are simply showing within these two groups which antibodies are different. That is statistically different in terms of the frequency of those antibodies or the numerical values of those antibodies in the two different cohorts. So there are quite a few that were different. So the first take-home message was, are these profiles different? Yes, they are. There are, I don't know, I'll count them up. All the red dots are statistically different between the two cohorts. This plot does not show which ones are higher in Libby versus Mount Sinai, but I can tell you that almost all of them were higher in Libby. So that's the other take-home point. Libby drives a lot more autoantibody production than chrysotile does. So at least that is similar between the mice and the humans. So we definitely see that. The other thing that he did was something called a random forest analysis, which I really like that name because it means you're not just looking at one tree. You're looking at the whole woods, right? So I felt like I was standing right in the middle of the woods when he explained this to me. This is one of these times when you sit down with the statistician and he explains it to you, and you go, yeah, okay. And as soon as I walked out the door, I had no idea what he was doing. All right. All good. Yeah, right? Okay, so these are the two, antihistone and anti-Smith, that differentiate these two populations. This is going to be of absolutely no value to us whatsoever because they're both found in lupus. But it's still interesting that this, after he did this huge analysis, this is what popped up. So the conclusions are that the autoantibody profiles are distinguishable comparing the two cohorts. But how predictive that's going to be is going to be extremely difficult to tease apart and might need more big data kind of analysis to look at this. The Libby cohort had a high prevalence of lupus-associated autoantibodies, which we knew from before. We've been doing this for almost 20 years. And antihistone was predictive for libby-amphibold exposure, which is interesting because antihistone antibodies show up in lupus, but also in drug-induced lupus. So there's an environmental driver for it. So maybe it's an environmental signature for autoantibodies. The steam fritter group had a lower overall values for most of the antibodies. Anti-Smith was predictive for this exposure. Anti-Smith can be almost diagnostic, correct me if I'm wrong, in lupus if it's found with other antibodies. But by itself, according to Marv, it's either non-pathogenic or there's no evidence of pathogenicity of these antibodies. So we're puzzled with that. He says you'd have to go drill down and look at the actual target for those antibodies, the actual epitope that these antibodies are binding to. So maybe an analysis of the subtypes. Quinta one time did an analysis of the subtypes of the mesothelial cell autoantibodies and found that the ones with chrysotile exposure were a very different IgG subtype than the Libby-Amphibold one. So that's another direction to go. Aim 2 of the study is in analysis right now. So from 2014 to 2019, we're finally getting the data. And what we're looking at here is trying to see if there are autoantibody profiles associated with the different disease types that we see in Libby. And so this is where we are right now. This is the data I just got this week. This is kind of a cloud analysis or a radar plot analysis trying to show the different autoantibodies. So here's all the autoantibodies, and here's all the people in the two cohorts. And what you see is a little bit different shapes of the peaks and what those peaks look like. So what they're analyzing now is the peaks and trying to show a difference with these diseases. And I'm no longer convinced that we're going to get anything real robust out of this. But we're looking. But at least we're looking. I think it was important to look, even though I'm not convinced that this is going to be a huge discovery. Maybe it will be, but I don't know. All right, this one was funded by the University of Washington Institute for Translational Health Sciences as an academic community partnership award between Brad and myself and Tracy. And what we wanted to do, the birth of this one was really, how can we help people downstream? I mean, really, what can we do to help people? This was the team, by the way, myself and my 2 undergraduate students, and Brad, Tracy, and Karenza. I can't say enough. Right now, I just would like to take a moment to say, wow, you guys. The CARD staff has been phenomenal. So that was the team. So what we have known is that exposure to LAA drives autoantibodies, and it also drives pleural fibrosis. But is there a connection? So that was really the big question. What is the evidence that the lamellar pleural disease that Brad was telling you about this morning, is it an autoimmune disease? Right? So that's the question here. What's the evidence behind that? So this is some work that we did back in 2012. And this was a project that I threw at a really, really excellent graduate student and said, hey, I want to know if there are any autoantibodies to mesothelial cells in people exposed to Libby-Amphibold. And I thought, may or may not be. Wow. That was exciting because what we found was, yes, there are antibodies to mesothelial cells. And this came out of a lot of work. There's been a lot of work done looking for autoantibody markers for mesothelial cancers and other things. But this one, I was looking for something that was driving the scar tissue, driving the production of collagen. So in this study, what this is looking at the ability of antibodies from the serum of the patients to stick to mesothelial cells. That is, to target them, to say, oh, you're my target, I'm going after you. So in the Missoula group, these were our normals. Again, this was the average binding ability of those antibodies to bind to mesothelial cells in culture. And this is what we saw in Libby. So what we did is take the mean of the normals, add 3 standard deviations, and that's the red dotted line. Above that line, the patients are positive for mesothelial cell autoantibodies, MESCAs. Okay? This is a pretty rigorous way of looking at this. You can do different standard deviations above the mean of a normal in order to produce a cutoff. We chose this one. You could choose others. So using that cutoff, around 35% of the Libby population have these MESCAs, whereas in this normal population, and then I went on to use a normal human serum set that I should give you, that I purchased commercially, and they were all down in here as well. So in just a screening population, I think this was from Missouri, the patients didn't have these autoantibodies. So this is our hypothesis. These patients are producing the autoantibodies. They bind to mesothelial cells. They change the phenotype of the mesothelial cells such that the cells are producing collagen. And they lay down this matrix, and that's the stuff of scar tissue. That's the stuff of fibrosis. So this is actually Quintas. So what she showed was in vitro, in cell culture, these cells produce collagen, which is what we're measuring on the y-axis, only if the patient is positive from that other graph for mesothelial cell autoantibodies. So just media, normal human serum, patients who are meskin negative but exposed, and then serum where we cleared out all the antibodies, so there's no antibodies left. None of those samples drove collagen production, but the patients who were positive for mesothelial cell autoantibodies, if you add that serum to these cells, they make collagen. That supported then this hypothesis that we're driving that phenotype change. And you've got now active collagen-making cells in the system. Kinta also did this. So I'm showing all of Kinta's work for her PhD, for her doctorate. She showed an association between radiographic pleural change and the presence of the mesothelial cell autoantibodies. And I love this representation because it's visual, and we can show it to students and they really get the idea. But this is just association. And then I can challenge them. Does this prove that these mesothelial cell autoantibodies are driving the scar tissue?
Can you just explain it more?
Sure. Yeah. So this is the subset of people that we looked at in the big circle. The red circle is people who had radiographic changes indicative of a pleural disease. The yellow oval is people who had radiographic change consistent with interstitial disease. And then everybody out here, no evidence, radiographic evidence of disease. So there's some overlap. I think there was a little bit of overlap between these two, but not very much. But then what she did was overlay the subjects who were positive for the mesothelial cell autoantibodies. And that was a 75% overlay right there. 75% of the people with the mesothelial cell autoantibodies had radiographic changes indicative of pleural disease. So where we went from this, just to explain why you're all so confused, Curtis and I then spent the next 5 years trying to replicate this in the LERP study, trying to show some association between the presence of mesothelial cell autoantibodies and pleural disease, and we failed to do so. So after a lot of discussions with Curtis and Brad, we decided to take a look at, let me just finish this. This is in mice. So we had the question of, this is association, not causation. Can we show causation? This is in mice. Can antibodies themselves cause fibrosis? We exposed a mouse to libiamphabol through the trachea for 7 months, took their serum, no asbestos, put that into the peritoneal cavity of a naive mouse, waited a month. Hypothesis: if the antibodies are there binding to mesothelial cells, which also line the peritoneal cavity, and if they're binding and making collagen, we should be able to find collagen in the peritoneal lining. So that's what we did. After a month, we took out the peritoneal wall and we analyzed that for collagen. And this is what we got. If the mouse was exposed to saline only, there's the baseline amount of collagen. There's always collagen in the peritoneal wall. And if they were exposed to chrysotile, that's the amount of collagen in the peritoneal wall. And if they were exposed to libiamphabol, there was significantly more collagen. Autoantibodies by themselves drove this. That told us that at least in mice, there's an autoimmune component to, in this case, peritoneal fibrosis. So, what does this all mean for patients? We want to look at long-term, what can we do to help people? So, can we have early detection for the risk of progressive disease? So Brad was telling you about these flares and the pain and the rapid progression that he sees in some of these patients that looks like an autoimmune disease. That's why I really appreciated your segue into this, is that there's pain, there are flares, there's musculoskeletal pain. There are things that make us think of an autoimmune disease in these progressive patients. So the way we designed this study was to look at the possibility that if we can determine an early detection for risk of this progressive disease, we might be able to find treatments to slow it down. That would be the big dream, to be able to do this. So then we start talking about screening in order to detect the risk of progression versus a more stable form of the disease. All right? So we've talked about some radiographic markers that we need to explore more, clinical and symptomatic markers that we've talked about. How do we get those into a database that's more numerical or quantitative, and then immunologic, and so that's where we're going to look today. I wanted to just mention the difference between a screening and a diagnostic test, which we'll hear a lot more from Claudia and Tracy later on when they talk about screening. But a diagnostic test obviously has to have a very, very high predictive value. You want to avoid false negatives that might lead to stress and excess testing in patients, and or false positives, and false negatives can miss disease. So you have to have a test that really nails it really, really well. Whereas a screening test can be a little bit softer. And this is a whole list of screening tests that I'm sure you're all familiar with that do not diagnose disease, but can give us an indication that further testing is needed. So that really is what we were looking for in this study, was to something that might lead to a more appropriate diagnostic so that we could pick up these cases early on. All right, so the objectives were first to create criteria to distinguish the different forms of Libby-lamellar pleural thickening. So we had the progressors, our symptomatic disease progressing to disability and death, and we have the CT scan that identifies the disease, and we have St. George questionnaire, and we have patient histories, et cetera, to identify these folks. Stable disease is generally asymptomatic or mildly symptomatic without progression, radiographic or symptomatic. They're not requiring oxygen, et cetera. And we've defined, Tracy and Krenza and Brad and I have very carefully defined these criteria, which I'm not going to go through with you, but I have them if you are interested. And then no disease group are folks that have no clinical or radiographic evidence of the pleural LPT. And then we're going to compare the serological profiles in terms of ANA, mesothelial cell autoantibodies, and anti-plasminogen. I haven't talked about that yet. This was a study we did that identified one of the epitopes. One of the binding targets for the mesothelial cell autoantibodies is plasminogen. So I wanted to do that test as well. And then we wanted to look at some cytokines that we thought might be indicative of autoimmune progression. And then the final thing was to determine whether any of the tests could be a screening tool that could predict a progressive clinical course for the disease. That making sense? All right. So this is just the exposure. So we used a lot of the data that's in the database to come up with exposures, and very, very simply what we did was we ranked them as high, moderate, and low. And this again goes to Krenza, who spent hours going through the patient's charts and the database to come up with their exposure profiles. Was it occupational? Was it environmental? Was it residential? How long did they live in Libby? How long did they work here, live here, et cetera? And came up with a score for them that ranked them as 3, 2, or 1. And so this is a kind of a sum of ranks test analyzed by Krusko, Wallace, and Nova to show that basically there was not much difference in the exposure in the 3 groups. A little bit higher exposure in the progressor group. That did come out as statistically significant, but not a lot. No difference between these 2 groups, statistically speaking. All right, here's the mesothelial cell autoantibodies that we've been talking about. This is the percent of the patients in this progressor group that were positive for the mesothelial cell autoantibodies. There's our 35% that we've been talking about. Stable group and the no disease group. This is statistically significant from both of these. Different. And then what we did was a mesothelial cell autoantibody score. And what that is the number of standard deviations above the normal mean that this patient scored on their MESCA test. So was it 2 standard deviations, 3 standard deviations, 4, sometimes 15, 16, 30 standard deviations above the mean in these patients in terms of their binding status. That's sort of a semi-quantitative amount of this autoantibody that they had. In that case, it broke out a little bit differently, where the progressors were higher than both the stable and the no disease group in terms of their score. So the amount of mesothelial cell autoantibodies is higher in the progressors. Break it down by sex. Brad, this is where you're going to have to step in and help me out here. All right. If we break the mesothelial cell autoantibody score by females and males, we see the pattern in the males, but we don't see it in the females. Couple of things here. There were only 6 females in the progressor group, so it's statistically weak compared to 13 in the males. The other issue is Brad has told me that anecdotally in the clinic, very few women develop the progressive form of the disease. So there's something here that's coming up in a study that I didn't expect to find it, showing a difference between males and females and their susceptibility to progressive lamellar pleural thickening. That's as far as we took it so far, but it's something to consider. This is the plasminogen, anti-plasminogen antibody, which is a member of the mesothelial cell autoantibody family, and it's Zach's job to continue to help us identify the other targets for these autoantibodies. So this fell out looking a lot like just the mesothelial cell autoantibodies in general that included these, in that the progressors were definitely the highest stable, but statistically, the no disease group was much lower in terms of this antibody as well. Males and females, same thing happened. We see it pretty clearly in the males, not so much in the females, which makes sense. We saw it with the mesothelial cell antibodies. It makes sense we'd see it with anti-plasminogen. This is Collagen Matrix. So this wasn't in the grant. This is something that my lab did just because I wanted to do it. This is the ability of the serum samples in the different disease groups to drive collagen production by the mesothelial cells in culture, like Kinta did before. So if we break this down, instead of just looking at the whole Libby population, let's break it down by the disease. So if we take the serum samples from the different disease groups, put them on the mesothelial cells, the serum samples on the mesothelial cells, and then look at collagen production by those cells, this is what we got. The progressors stimulated more collagen than even the stable group, and then the no disease group. But the no disease group was significantly different from both of these. So with no disease at all, they lack these autoantibodies, or the autoantibodies are not functional in terms of producing collagen. So although this would probably not be a great screening test because it's a difficult assay, it's time consuming, technically difficult, probably wouldn't necessarily want to do it in the clinic, it indicates a mechanistic basis for the efficacy, potential efficacy of MCAA screening. These are the 2 cytokines. I'm going to spend too much time on this. Basic, and look at IL-17. This is in females and males. Absolutely no difference between the groups. IL-17 is not going to give us any information about screening for these different disease phenotypes. IL-1 beta was interesting just because there was nothing in the males, but in females it looked kind of interesting. But again, this is only 6 of the progressors were females, and this is how this showed up, so we would need to do a lot more work there. Obviously, it's not going to be a general marker for a population because it doesn't help with males. All right. Finally, drum roll, the ANA screen. So anti-nuclear autoantibodies were the strongest data associated with progressive lamellar pleural thickening in these groups. So this is the progressors, the stable patients, and the no disease patients in the females, progressors, stable, and no disease in the males. So the next thing that we had to do was, this was part of the grant, we had to look for sensitivity and specificity. So how many of you know all about screening, specificity, and sensitivity? All right, 3 of us, and barely that, because this is all very, very new to me, so I'm no expert. For testing for sensitivity and specificity, sensitivity tells you how well a test correctly identifies a patient with a disease. All right, so if it's a really good test, a positive test will predict for progressive disease. In other words, the patient gets a positive test, you can say, all right, you're at risk for this progressive disease. Specificity tells how well a test correctly identifies patients without disease. That is, like, rule them out. Say, all right, you don't have much risk for progressive disease if you get a negative test. So between the two things, sensitivity and specificity, you can get kind of a predictive value. The problem with predictive value is that it's usually set on one cutoff point, positive, negative cutoff point. How sensitive is it at this cutoff point? So we have different cutoff points for ANAs. We have 1 to 40, 1 to 80, or 1 to 80, 1 to 160. Where's our cutoff point? So then you go to this receiver operator curve analysis, where you get a curve on the graph from looking at several different cutoff points. So for ANA, we used 1 to 40, 1 to 80, 1 to 160, 1 to 320. For the mesothelial cell antibodies, we used 2 standard deviations above the mean, 3, 4, and 5. So different cutoff points, create a curve, and look at the area under the curve. And what that's going to give us is using different cutoff values to calculate the screening accuracy, how well it predicts for this disease. So this is what we did. This is data for the progressor group only, looking at how well any of these tests serve as sensitivity, specificity, predictive value, and the area under the curve for ROC analysis. What you can see is that sensitivity is relatively poor. Interestingly, IL-17 came up as saying if you've got IL-17, you probably have progressive disease, but unfortunately, it doesn't rule out people without disease well at all. But really, our sensitivity wasn't very good, meaning that if a patient gets a positive ANA test, it probably doesn't predict that they're going to get progressive disease. But the specificity, the ability of a negative test to say, no, you're probably not going to get disease, is pretty good. Anytime you're over about 75%, you're looking at a pretty good prediction, being able to say, all right, we don't think you're going to progress to this more severe form of the disease. There are the predictive values, and again, the negative predictive values are higher than the positive predictive values. And these are the ROC curves. This is where we looked at several different cutoff points for positive and negative. Anytime you're over about 0.6, they call it a fair test. Over 0.7 is a good test. Anywhere close to 0.5, 0.6 and below is going to be fair, and anywhere below 0.6 is called a poor test. It's not predictive at all. You're pretty much close to just 50-50 on that test. So we're looking at a couple of fair tests here that have pretty good specificity, and these two are related. So plasminogen is a mesothelial cell autoantibody, so it makes sense that they're similar, and collagen is not a very good screening test just because of the technical difficulties involved in it, but that one's similar as well. So I wanted to look more at those two. This is a graph, the same thing, looking at if we are just progressing or predicting for lamellar pleural thickening at all, whether it's stable or progressing. So I combined those two groups, the progressors and the stable group, and did the analyses, and we end up with fair, 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 poor, poor, poor. The test is much worse if we're just predicting for disease. So these antibodies seem to be much more specific for the progressive form of the disease, which helps me deal with what Curtis and I dealt with the ALERT project, was that we could find no association between the autoantibodies and the presence of any disease. So, very briefly on combination screening, it's possible to do 2 tests, so we do that a lot with different combination screenings where you do one test and then another, and you can do either a 2-stage combination screen where you do one test and then you follow up with a second test. Or you can do a simultaneous screen where you go ahead and do both tests without knowing whether one's positive or not. And so you get different information, but basically I crossed ANA screening as our first screen with either the MCAA or the PLG. We got the same information from both of these. Specificity goes up to about 98%, meaning that if they're negative for both of these, they are probably not going to progress. And then a simultaneous screen, sensitivity went up into the 70s, which gave us a better ability to do a positive prediction of disease if they were positive for both tests. So including 2 tests might improve the screening process. It's something that we might look at in the future, starting out with just ANA screening. I did look at including the IL-17 in there just because a reviewer might see that high sensitivity with IL-17 and say, well, what about using that? And I went, yeah, sensitivity goes up, but specificity just bottomed out. So ANA testing, even in this small subject group where we had 19 progressors and 38 each of the stables and the no disease people, it's a pretty small group, we were able to identify a potential screening tool for progressive lamellar pleural thickening. Mesothelial cell autoantibodies and the plasminogen antibodies also were predictive, sometimes only in males. Females were a small subset, so that would be something we'd have to think about in terms of its value to us. But combining either of these tests with ANA screening may be of value. No marker had value in predicting stable LPT or a combination of either or stable or progressive LPT. So that helps explain the LERP data, which really frustrated me. Cytokines were of very little or no value in predicting disease progression. One of the biggest outcomes from this study that I'm really glad we did this was it helps me to begin to look at the mechanisms of the progressive pleural disease that, as Brad has said, looks like an autoimmune disease, feels like it to the patients in the way that it progresses, in the way that they feel systemically. So I think this is a really important step forward in just helping us understand the mechanism of the progressive disease. So with that, just ending up with some really cool pictures from Libby. This is John Gilmer, who did, along with Kinta, the studies in the mice showing the peritoneal fibrosis. And Laura Linker, who couldn't be here this week, which is very, very sad. Brad and me having way too much fun. And Kinta and I at Mount Sinai in 2013. This is before we even thought it was, so it was a while ago.